Hello friends, welcome back to my channel Chemistry Unplugged. So it is second part of organometallic compound, and in this chapter we will take 18 electron rule. What are the key points, or you can say important points for this rule, or what it predicts. We will take many examples which will be helpful to you. And we will also discuss 16 electron rule. What is 16 electron rule? And some exceptions to both 18 as well as 16 electron rule. And if you want any update about organic chemistry, you can follow me on Unacademy using my name, or you can use this link also. So before starting the video, please subscribe to my channel and click on bell icon for future notifications. So let's start the video. So 18 electron rule. What 18 electron rule says? 18 electron rule says that organometallic compounds or transition metals having 18 electrons are stable in nature. It defines stability of organometallic complexes. And what is the meaning of why we are taking 18 only? Because if you see that NS2, NP6 and D10, the total will be 2 plus 6, 8 plus 10, 18. So if a metal ion is stable, means it does not want any electron, or it will not give its electron. It occupies a stable configuration only in the situation when it has 18 electrons in its outer shell. So how to calculate 18 electron in organic metallic compound? First, we should have knowledge about the electron contributions by the different ligand, and we have already discussed in first part what is the electron contribution by the different ligands, and we are following neutral rule because it is more easier. So first we should know number of electrons contributed by ligands. What are the contribution of electrons by ligands? Then we need what is the number of electrons in outer shell of metal ion. So we will take different metal. This is these all are transition metals, and you should have the knowledge about the number of valence shell electron in all these metals. So you should memorize these all metals. So scandium, we will start with scandium. Scandium has 3 electrons in its outer shell. Then titanium has 4, vanadium 5, chromium 6, manganese 7, Ns2, Np7, iron 8, and cobalt 9, nickel 10, and copper 11. We have to memorize these second row metals also: yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, and silver. And third row also. So first you have to memorize the number of valence shell electrons in all the elements. So I suggest first you try to memorize first row and then group wise. Then it will be easier. Then we will take some important points. Important points are that complexes which have 18 electrons in their outer shell are stable in nature. First point is this. But if suppose some organometallic complex has 17 electron in its outer shell. So what will happen? 17 electron means it wants some electron. Okay, and when it occupies some electron or captures some electron, its oxidation state will be reduced. Means in the starting, suppose it is N, after accepting electron it will become N minus 1. So there is reduction, means it is acting as a strong oxidizing agent. So the complexes which have electron less than 18 electron, means 7 or 16, are acting as a strong oxidizing agents, while complexes which have higher electrons than the 18 electrons will try to donate their electrons, and in that case their oxidation will take place and they will act as a strong reducing agent. Means suppose M is now having 19 electron in its valence shell. It will try to give its electron. So after giving its electron, its oxidation state will be increased, means its oxidation takes place, so it will act as a strong reducing agent. Then complexes having 17 and 19 electrons are paramagnetic in nature. Paramagnetic in nature. While complexes having 18 electrons are diamagnetic in nature. First is this iron complex. So we will try to calculate number of electrons in total in this complex. So iron is having 8 electrons. Okay. If you look at this table, iron has 8 electrons in its valence shell. So 8 electrons will be contributed by iron, and this is cyclopentadiene, and we know that it is in eta 5 state, means all the 5 carbons are contributing towards this central metal. So 1 Cp is providing 2, so 2 will provide 10, means it is following 18 electron rule. Then we have FeCO5. So Fe again 8 electrons in outer shell. 1 CO gives 2 electrons. So 5 will give 10. It is also following 18 electron rule. Then we have this complex of manganese. Manganese has 7 electron in its outer shell, and methyl will provide 1 electron. We know that alkyl provides 1 electron. Okay, and CO will give 2 electrons. So 5 CO will give 10 electrons, and 1 is by methyl group, so it is also following 18 electron rule. Now we have this complex of iron. Cp is an N5 state, means eta 5 state, means it is providing 5 electrons. Iron 8, 2 CO means 4 electrons, and 1 by this Cl. So it will become 18. So it is also following 18 electron rule. Now we will take some more example. So this is a complex of cobalt, and cobalt has 9 electron in its valence shell, and Cp, the hapticity of Cp is not given, so we will assume highest hapticity, means it is providing 5 electrons. So 5 into 2 plus 9. Now this complex has positive charge, means it has to give one of its electron, so we have to minus 1, so total will be 18. So it is again following 18 electron rule. Then we have iridium. Iridium belongs to cobalt family, so it has 9 electron in its valence shell. 2 is given by this ppH3, lone pair of electron by phosphorus, and 2 by this one, plus 1 by Cl, and CO will give 2 electron. The total will be 16 electron, means it will accept electron, so it will act as a strong oxidizing agent. Then we have this ruthenium complex. It is known as Grubbs catalyst. Very important example. So ruthenium belongs to iron family. So it has 8 electron in its valence shell, 2 by this, 2 by this, and 2 by this alkene, 1 by each Cl. Then the total will be 8 plus 2 plus 2, 4, plus 2 and plus 2. So it is also has 16 electrons. So we have already discussed in previous video about the oxidation state, how to calculate oxidation state of all these complexes. So if you have any doubt, you can see that video again. Now we'll take this complex of molybdenum. It should be like this. So molybdenum belongs to chromium family. So molybdenum has, so in this example, molybdenum will provide 6 electron. It belongs to chromium family. It has 6 electron in outer shell. Allyl will provide 3. This Cp will provide 5, NO in bent state, so it will provide 1, and this NO is in linear state, so it will provide 3. So the total will be 18 electron. Then this chromium complex, chromium has 6 electron in outer shell, 2 provided by each of CO, so we have 5 CO groups here, so the total will be 10, and this carbene will provide 2, so it also has 18 electrons. Then we will take this tungsten complex. Tungsten is also belongs to chromium family, so it has 6 electron in outer shell, and these alkoxides will provide 1 electron. This carbene will provide 3 electron, so it is following, it has 12 electrons only. Now we will take this ruthenium complex. This ligand is dimethyl phosphino methane. So it has a structure like this. It is phosphinoethane actually. So in this ligand we have 2 phosphorus atoms, so each will provide 2 electron. So the total contribution towards metal, that is ruthenium, by one ligand is of 4 electrons. And if you try to find out its formal charge is 0 because it is a neutral ligand. So formal charge is 0, but electron contribution is of 4. So here we have 2 such ligands. So the electron contribution will be 8. And ruthenium belongs to iron family. So it has 8 electron in its valence shell. So 8 electron in ruthenium. 4 is provided by 1 dimethyl phosphinoethane. So 4 electron is provided by one ligand and 4 is provided by other, because we have 2 diphenyl phosphinoethane here. So the total will be 16 electrons. We can also have here dimethyl phosphinomethane. So it is also similar to this one. It also provides 4 electron. Electron contribution is 4 and formal charge is 0. You can write it also like dimethyl phosphinomethane, DMPM, or you can have here pH group also. So this will become diphenyl phosphinoethane. Diphenyl phosphinoethane. Its electron contribution is also 4 and formal charge is 0. Now we will take these 4 complexes and you have to find out that which one is following 18 electron rule or which one is not following. So first we will take this one. Cp is, the hapticity is not given, so we will consider highest hapticity. So it will contribute 5. Ruthenium belongs to iron family, so it will provide 8 electrons. Then 1 Cl and 2 by this CO, 2 by this PPH3. So the total will be 18. So this one is following 18 electron rule. This is correct. Then we have tungsten. Tungsten belongs to chromium family. So it has 6 electron and here we have 3 CO. 1 CO provides 2 electrons, so 3 will provide 6. Then we have SiMe3. So you can compare SiMe3 with CMe3 because carbon silicon belongs to same group. So carbon will also provide 1 electron. It is similar to carbon, so it says silicon will provide 1 electron and its formal charge will be -1. It is similar to alkyl group. So it will provide 1 electron. 1 is provided by this Cl and here we have NCMe. MECN. You can also write it like this. So this is, it will provide 2 electrons from this nitrogen and we have 2 such ligands, so it will become 4. So the total electron count will be 6 plus 4, 10. and this is also following 18 electron rule. This is also following. Next we take iridium complex. So iridium belongs to cobalt family. So it has 9 electron in its valence shell, 3 by this 3 Cls, 1 by each. So it will become 3. ppH3 will provide 2 electrons. We have 2 ppH3, so it will become 4. Then we have AsPH2. So you can compare arsenic with nitrogen because both of them belongs to same group. So you can write it like Nr2. So when we have Nr2 means it has -1 charge. So it will provide 1 electron. Similarly, it will also provide 1 electron. And this complex also has -1 charge. So we have to add this one. So total will become 18 electron. Then we have osmium. Osmium belongs to iron family. So osmium will provide 8 electron and nitrogen will provide 3 electrons. Then we have bromine. Similar to other halogens, it will provide 1 electron. So we have 2 bromine here. So they will provide 2 electron. Then we have PMe3. So it will provide 2 electrons. And NMe2, it will provide 1 electron. Then this complex has -1 charge. So we have to add +1 here. So the total will be 8 plus 2, 10, 16, 17. It has 17 electrons. Means this one is not following 18 electron rule. So you can find out like this that which complex is following 18 electron rule or not. So for this you have to know about the number of valence shell electrons in the metals and the electrons contributed by the ligands. Then it is very easy. Then we will take some more complexes, and these examples are a little bit different. In these, it is given that they are following 18 electron rule. All the complexes are following 18 electron rule. You have to find out N, Z, and M in this case, and M in this case. So we will take them one by one. So first we will take first. So chromium has 6 electron in its valence shell. Eta 3 C5H5 means it is providing 3 electrons. Okay, it is in 3 state. CO will provide 2 electrons, and here we have NCO. So we can write it like this. And CH3 will provide 1 electron, and it is following 18 electron rule. So first we will count this. 2n is equal to 8. So n will become 4. In next example, you have to find out the charge on the complex. So we have ruthenium here. Ruthenium means it has 8 electron in its valence shell, belongs to iron family. CO will provide 2 electron. We have 4 CO, it will become 8. And SiMe3 will provide 1 electron. Then we have this charge Z. So we will first add it as it is. Okay. Then we will place it equal to 18. Then Z is equal to 1. So means if you are adding this 1 in the all the electrons, then you will get 18 only. Means this charge should be -1. Only in that case you can add in the total, means only in that case this electron will be added in the total electron count. So it should be -1. Then we have third example in which you have to find out M. What is M? So first we will write M as it is. Then CO will provide 2 electrons. So we have 14 electron plus 1 means we have to minus 1 electron, and it is equal to 18. It is given. So M will become 5. Means M should have 5 electron in its outer shell. And 5 electron means if you write it like this, 3, 4, 5, 6, 7. Then first you have scandium, then you have titanium, and 5 means you have vanadium. And if it is given that you have to find out the metal from the first row, then you will answer vanadium. But if they say that you have to find out from second row, then in case of scandium, next we have yttrium, titanium is zirconium, hafnium, and in case of vanadium we have niobium and tantalum. So answer will be niobium in that case. In next example, we again have to find out M. So first we will write M as it is. Then 2CO means total will be 4 electron. Then CS means CS is also similar to CO. So it will also provide 2 electrons. 2 electrons. Then PPH3 will provide 2 electron and Br will provide 1 electron. And total is equal to 18. So M will become equal to 4 plus 2, 6, 8, 9 and it will become 9. Means it has 9 electron in its valence shell. So we can again write it like this. We have vanadium, chromium, manganese, iron and then we have cobalt. And in cobalt family, in first row the answer will be cobalt. Okay, but if they are asking you the second row, then after cobalt we have here rhodium and then we have iridium. So from the second row answer will be rhodium, and if they ask you the metal ion from the third row, answer will be iridium. So you should have knowledge about all these elements or their valence shell electrons. So this is all about these questions. Then we will take some more question. Okay, in this question they give you 4 options and you have to find out that which complex is stable. You have to find out which one is stable. So stability means you will try to find out 18 electron rule. But if you look at the central metal atom, it is not a transition metal. It is a S block element, means it is following octet rule. Means it should have 8 electrons in its valence shell. Means it is following octet rule, means the total should be 8 electron. Okay. Now we will try to calculate number of electron in each complex. So in first we have beryllium. So beryllium in the outer shell, if you count the electron in the outer shell of beryllium, it is 2. And CFH5 means we will consider 5 hapticity. So total will be 10. So it has 12. It is not stable. Then we will take second one. Again beryllium is 2. This is 5. If it is given, then we will take 5 and 3 means we will take 3. The total will be again 10. Then we will take third one. Beryllium is 2 and Cp is with 1 hapticity, so 1 electron contribution and 3 by this one. So the total will be 6. Then we have fourth one. In fourth we have 2 plus 1 plus 5. It has total 8. Means this is the most stable complex of beryllium. So this is the correct answer. So next we will take 16 electron rule. What is the meaning of 16 electron rule? Some complexes follows 16 electron rule and their stability is defined by 16 electron rule, and this rule applies on square planar complexes. We will take some examples of this, which complexes are following 16 electron rule. So these two complexes are very important example. They are following 16 electron rule. They are square planar complexes, and this complex is also known as Z salt. Then we will take some exceptions to 18 and 16 electron rule. These complexes have electrons less than 18 and 16 electrons, but still they are stable. They are stable because of the presence of some ligands which are highly sterically hindered, and you cannot add more ligand or more electron to such type of systems, and they are stable with the less electrons. So the examples of these type of complexes are. So this is all about 18 and 16 electron rule. Thank you so much for watching. In next video we will take how to calculate metal-metal bond and what are the bridging complexes. Keep watching. Please like, share my videos with your friends, and please subscribe to channel. Thank you so much.